Good morning, students. Today is our second lesson on chapter 6, Geometrical Optics. And today we will see more about refractive index. You already have some idea about refractive index because in the last class we saw what is reflection and what is refraction, and we have also seen refractive index. Now we will find a relation between refractive index of different medium, and then also we will derive an expression for Snell's law, a general form. So what is meant by refractive index? When light enters obliquely, what is meant by obliquely?
There will be an angle.
Making an angle less than 90 degree. Less than 90 degrees called obliquely to a transparent medium from another transparent medium. Then for a fixed pair of media and for a fixed color of light, the ratio of the sine of angle of incidence to the sine of angle of refraction always remains constant. And this constant is called the refractive index of the second medium with respect to the first medium. So in lower class, you must have learned situations where the light usually enters from air or vacuum to another medium, and you took it as a refractive index of that medium. Suppose light is entering from two transparent mediums. For example, light is entering from water to glass. So they are two different medium, right? So here you can see a picture here. Let this be medium A and this be medium B. And light from the incident ray is coming from medium A and it is passing to medium B. So the refractive index of the second medium, that is medium B, with respect to the first medium is equal to sin I by sin R. So this is called the relative refractive index. Relative refractive index of medium B with respect to medium A. That is equal to sin I by sin R. And refractive index of a medium can also be expressed in terms of the velocity of light. Have you learned this before? How to express refractive index in terms of the velocity of light? Have you learned it before?
So this equation,
Yeah.
yeah, I guess we learned
Velocity of light in the
medium.
first,
Yeah.
velocity of light in medium A, that is the first medium, which is represented by CA, divided by velocity of light in medium B. So here, what do you call this? This is the refractive index of medium B with respect to medium A. That is the refractive index of second medium with respect to the first medium. So you know what is relative refractive index, right? What is it? How will you read this? Bibi, can you read this? Mu BA means what?
Mu A mu B, right?
Medium A to medium B.
Medium A to
Medium
medium
B
A, or how will you tell that? What is this in terms of
with
refractive index? Refractive index
refractive
of,
index of medium B with respect to medium A.
yeah, this is the refractive index of medium B with respect to medium A. And when you write in terms of velocity of light, you have to write the first medium in the numerator and second medium in the denominator. And also when you say sine of the angle in the first medium divided by sine of the angle in the second medium. So this is relative refractive index. And now when we discuss about the absolute refractive index of a medium. Now, absolute refractive index is also called just refractive index. Now, this occurs whenever light travels from air or vacuum to a medium. So when light enters obliquely to a transparent medium from vacuum or air, then for a fixed color of light, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is called the absolute refractive index of that medium for that color. So if you just represent mu, that will be the refractive index of one medium with respect to air. So you have to write that as a velocity of light in vacuum or air, because light is coming from air and going to a medium. So divided by velocity of light in that medium. So air is the first medium, and water, glass, or any other transparent medium is the second medium. So the point to be noted is that the refractive index does not depend upon the angle. It does not depend upon the angle of incidence or the angle of refraction. It's the property of a medium. So even if you change the angle of incidence, correspondingly, the angle of refraction may change, but it doesn't affect the refractive index. It is a fixed value for a particular medium and for a particular color. So refractive index does not depend upon the angle of incidence, but it depends upon the pair of medium and also the color of light. Can you tell me which color has minimum refractive index? Which color has minimum refractive index?
Red.
Red. Red has minimum refractive index, and there will be maximum refractive index for violet light. So when light is entering, you must have seen a figure where when light travels through a prism, it gets separated into different colors. Do you know why? Why it separates to different colors?
No, teacher.
It separates to different colors because each color has got a different refractive index for the prism. So each of them will have a slightly different angle of refraction depending upon the refractive index. So each color has got a different refractive index. So the color with minimum refractive index will deviate less, while the color with more refractive index will deviate more. So violet will deviate more, red will deviate less. That is why when they pass through a prism, different colors get separated. We are sending white color light with the same, all the colors when they are coming as a white light, they are coming together with the same angle of incidence. But when they pass through the prism, each one will have an angle of refraction depending upon their refractive index. So for different colors, the refractive index for that particular prism will be different. That is why they are getting separated into colors. And the minimum is for red light, so it gets deviated minimum, and maximum is for violet light, so it gets deviated more. So violet you will get at the bottom and red at the top. So that is why they get separated when they pass through a prism, because each color has got a different refractive index. Later in this chapter, we will find how to calculate the refractive index for each color. Now, a medium with high refractive index is called optically denser compared to a medium with low refractive index. If the refractive index is low, we call that it is optically rarer. But this optically dense and rare has nothing to do with physically dense and rare. Let me ask you a question. Kerosene oil, water, which is more dense?
Water.
Water is more dense. Why?
Because the density of oil is less.
Hmm? That is why when you make a curry and something, the oil will be on the top, right? And even on a rainy day, if there are puddles of rain on road, and when some petrol or something or oil gets split from a car, it will stay above the water. You can see that. So all that is because water is denser than oil. That is physical density. But optically, we can say that oil is more optically dense than water. So optical density and physical density is not the same. Optical density depends upon the value of refractive index. So for air, the refractive index is taken as 1, and for other quantity, all other material, the refractive index will be greater than 1. And optically, I'll tell that oil is denser than water. So which will have more refractive index, oil or water?
Oil.
Oil will have more refractive index. So optical dense and physically dense are different concepts. Okay, so
They're
don't
opposite,
confuse.
right?
What?
They are opposite to each other.
Not opposite. We cannot, there is no proof that they are related in a different way. Okay, so we cannot confirm now that they are opposite, but I just told you one example, it is not same. Okay, so let us see now a relation that the refractive index of one quantity divided by the refractive index of other quantity is equal to this. That is, if you have two medium, B and C, and light is coming from B to C, then the refractive index of medium C with respect to medium B is equal to absolute refractive index of C divided by absolute refractive index of B. And I will show that on whiteboard. So I just want to stop sharing this screen, and we will derive this expression on a whiteboard. Okay, can you see the full whiteboard now?
Yes, teacher.
Yes, teacher.
Okay, so we are here to derive an expression that the refractive index of C with respect to B is equal to refractive index of B divided by refractive index of C. Okay, where C and B are two medium. And we know that here the condition will satisfy when light is entering from B to C, right? So let us consider a situation where there are three medium. Medium A, medium B, and medium C. Let light enter from medium A to B with an angle of incidence I. Okay, light is entering from medium A to B with an angle of incidence I. Now, after refraction, suppose it makes an angle of refraction R1. This is one refraction. Again, the same light enter from medium B to medium C. So it is making another angle of refraction, say R2. And again, it is coming from medium C back to A. Suppose you have here, I will give a physical example. Suppose this is air, and you have a vessel which is made of thick glass containing water. So light will enter from air to water, then to glass, that is the container, and then back to air. So suppose that is a situation. And here again it will get back to air. And when light emerges out, this is called emerging light. This is called the incident light. After passing through two medium, it is emerging out. Emerging. Always the angle of incidence will be equal to the angle of emergence. So I can put it as also equal to I. So if it is entering with angle I, if it is emerging to the same medium, then the angle will be I itself. Angle of incidence will be always equal to angle of emergence. So this is this equation. There are three medium. Is that clear to you?
Yes, teacher.
Okay. Now, suppose this is R1. I told R1, right? Now you have two parallel lines and these two are two normal. So what will be this angle? Alternate interior angles you can call, or opposite angles. They will be same. So if this is R1, this will be R1. And what will be this angle? What will be this angle? If this is
180
R,
minus R1.
what?
No, no, no.
Is this
No.
figure clear
R2.
to you? Should I draw it bigger? See, these two are two parallel lines. And this is one line cutting that. These two are normal. So what will be this angle? This is R2. So what will be this?
R2.
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 R2. Okay. Now we are going to write the Snell's law for each of these three refractions. Okay. Tell me Snell's law for this refraction. What is sine I by sine R1? What is sine I by sine R1? Is equal to refractive index of the second medium with respect to the first medium. So we will write it as mu B with respect to A. Because light is entering from A to B, right? So sin I by sin R1 is equal to refractive index of B with respect to A. Now similarly, when I take the second refraction, I'm writing here the angle of incidence is R1 and angle of refraction is R2. So sin R1 divided by sin R2 is equal to refractive index of the second medium with respect to first medium. So it will become mu C with respect to B. Now, again, I can write the Snell's law for this refraction. So, what is sine? Angle of incidence here is R2. Sine R2 divided by sine I is equal to refractive index of the second medium with respect to the first medium. So, mu A with respect to C. Are these three equations clear to you? These three comes directly from Snell's law.
Yes, teacher. It's clear.
Now, what I am going to do is, I am going to multiply these three equations. Let us see what will happen. Sin I by sin R1, sin I by sin R1 times sin R1 by sin R2 times sin R2 by sin I equal to mu BA times mu CB times mu AC. Okay. Here sin I and sin I gets cancelled. Sin R1 gets cancelled. Sin R2 gets cancelled. So what is this? This will become equal to 1. If these two cancel, 1 times 1
1.
times 1. So here you have 1 is equal to this. What is that? Mu BA times mu BC times mu CA. Now here we want mu CB is equal to refractive index of C with respect to B equal to. So I am taking this in one side and taking the other to the other side. So we have mu CB is equal to 1 by mu BA times mu CA. Is this clear? Now, I can write mu AC as 1 by mu CA. I can write here this is mu AC, right? This can be written as equal to 1 by mu AC. Did you understand how this happens?
Yes, teacher.
So how did this happen?
Here,
It's a formula, right?
entering from A to C. Okay. And here, this will be, if light is entering from A to C, then what happens? This will go in this way. Here we have, where is this? Okay. Mu AC. Mu AC means light is entering from A to, C to A, like here. Light is entering from C to A. So we have sine R2 by sine I. Now, if the reverse happens, that is, if light comes from, if this is the case, then light will be entering from A to C. So what will be the
Teacher.
relation?
Understood.
Sine I
It will be inverse.
sine R2. So it's the inverse.
Inverse.
Okay, so I can write this as the inverse of this. So if I take this to the numerator, I just have to switch these two, A and C. So I can write this as equal to mu CB is equal to, instead of 1 by mu AC, I am writing mu CA divided by mu. Okay. Did I make a mistake? Yes, this should be CA. I wrote it as AC. That is the mistake. Mu CA. So mu CA, 1 by mu CA, I can write it as mu AC. So I am writing it as mu AC. And here what is remaining? Mu AB. Is this clear? Mu BC is equal to mu AC by mu AB.
Yes, teacher.
Now, suppose the first medium and the last medium are air. And this two are any two medium. For example, this may be glass and this may be water. Or the other way, whatever. Oh, I told for an example the other way, right? Whatever be the case, any two medium, water and glass. So when light enters from air to water, then mu AB is mu B, the absolute refractive index of water, or absolute refractive index of B. So I can write this as equal to mu B. And when again light is entering from air to glass or any medium C, it will be the absolute refractive index of that medium. So mu C. So I will get it as equal to, oh, I got it in the other way. Let me just confirm. Yeah, I wrote here the question wrong. Should be C by B itself. So it should be, where is it? So mu AC by mu AB. So we got it as mu CB is equal to mu C divided by mu B. Is this clear to you?
Yes, teacher, clear.
Is this clear to you? So you may be asked, I wrote the question wrong on the whiteboard, I'm sorry. But mu CB, that is refractive index of C with respect to B, is equal to refractive index of C divided by refractive index of B. Now, for example, I have the refractive index of glass with respect to water. Suppose light is traveling from water to glass. Then what will be the relation? Can you tell me?
Mu glass by mu water.
Mu glass by mu water. So if light is entering from any two transparent medium, this is how the relation between the two mediums refractive index will be. So you will have to use this idea in the equations to solve numerical problems. So they may give you the refractive index of glass and water, and the situations will be like one is traveling from other to this, and you may have to find out the angle of refraction or angle of incidence. So you will have to use this idea according to the situation. So is this clear to you? Now we will use this idea to get a generalized equation for Snell's law. What is Snell's law? Who can tell me Snell's law? Khadija, can you tell me Snell's law? What is Snell's law?
At a fixed color,
For a
the
fixed
sign
pair
of
of medium and fixed color. Yes.
the sign of refracted, the sign of incident angle. Yeah, the sign of incident angle is divided by sign of
Is
refracted angle.
equal to is
Constant.
Constant.
equal to a constant,
Constant.
and that constant is called the refractive index, right? Suppose we have two medium 1 and medium 2, and the light is entering from one medium to another. Okay, so here the angle of incidence is I, angle of refraction is R. So sin I by sin R will be equal to mu. What should I write here? 1 or 2?
2,
2. Here
1.
1. So refractive index of the second medium with respect to the first medium. So according to this relation, what will be this equal to? What should I write in the numerator?
2 by 1.
Mu 2 by mu 1. Okay. Now I'm going to cross multiply these two. Cross multiply these two. So what will it become? Mu 1 times sin I. Mu 1 times sin I is equal to mu 2 times sin R. Okay. Now, let me express the angle in this medium as theta 1. And I am expressing the angle in the second medium as theta 2. So I can write this expression as mu 1 sine theta 1 is equal to mu 2 sine theta 2. This is called generalized Snell's law. This is called generalized Snell's law. Why? The light can be traveling from any medium to any medium. Maybe it's traveling in this direction. It may be traveling in that direction. Doesn't matter at all. What you can know is that refractive index of one medium times sine of the angle in that medium is equal to refractive index of this another medium times sine of the angle in that medium. That's all. So you don't have to care light is traveling from where to where. Doesn't matter. What you can do, the refractive index of that particular medium times the sine of the angle made in that medium will be a constant. That's all. See here, in one particular medium, in medium B, the angle made both places are the same, R1. So you can write mu B into sine R1. Doesn't matter, light is traveling from here to there or there to here, doesn't matter. So you can write from here mu B times sine R1 is the angle in that medium is equal to mu C into sine angle made in that medium is R2 is equal to mu A sine angle made in that medium is I. That's all. Okay, so it doesn't matter from where light is coming or going, but refractive index of that medium times sine of the angle in that medium is a constant. Is that clear to you? Is this a simple way to learn Snell's law?
Yes, teacher.
Okay, so whenever you do problems, just take care. It doesn't matter light goes from where to where. Refractive index of that medium times sine of the angle in that medium will be a constant. Okay, that is called Snell's law. So today we have just discussed the refractive index of different mediums and also the Snell's law, its generalized formula. Now, there are just 2.5 minutes left. Do you know what is meant by total internal reflection? Have you already learned what is total internal reflection? Can we discuss that now or should we go for the next class?
Better next class.
Okay. So just who can tell me what we learned today? South, can you tell me the relation between refractive index and velocity of light? South, tell me what is refractive index? How is it related to velocity of light? Refractive index of a medium is equal to Is there any problem with South's microphone? Okay, yes, I can't hear you, South. I know you are talking, but I can't hear you. Rifat, tell me what is the relation between refractive index and velocity of light? Rifat.
Yes, teacher.
Yes, what is the relation between velocity of light and refractive index?
Velocity of light in vacuum
Velocity of light in vacuum divided by
velocity of light in the medium.
velocity of light in the medium. Right. Now, who can tell me generalized Snell's law? Fahima, can you tell me generalized Snell's law?
Can I say
Yes, yes.
mu1 sin theta 1 is equal to mu2 sin theta 2?
Mu1 sine theta 1 is equal to mu2 sine theta 2. Okay. Now, Mariam, can you tell me what is relative refractive index? When light travels from glass to water.